What's up, guys? Mr. C here with lesson 8.5. Going to be going over simple harmonic motion. Basically, simple harmonic motion are things that can be modeled using our sines and cosine waves. Just kind of a quick animation for you guys to take a look at this thing here. Let me go back to the beginning. So notice the spring. This can be modeled in like circular motion as well, things that vibrate. But most likely, we're going to be doing problems with springs today. Notice that the position of the ball on the spring as it goes up and down kind of models a sine wave. So we're going to be using that to be solving some problems today. We are going to do some recap from chapter 6, like the parts of my graph of the sine and cosine function. But just go ahead, we'll let the animation, oh, it's done. So yeah, hope that kind of gives you a sense of what we're doing. So let's go ahead and look at it. So if you recall, our equations for sine and cosine, they're going to be looking a little bit different just because we're doing applied problems. So rather than y and x, we're going to be using d and t for distance and time. So we have our two equations. The first one, d is equal to a times cosine of wt. And then it's the same thing for sine. A times sine times wt. All right, remember that the height of the wave, or the amplitude, this is going to be, and we say the absolute value of A just because it's amplitude. We always write that as a positive value. And then the period of the function. Remember, the period was how long does it take for the wave to complete itself, okay, or to repeat itself. Like from 0 to 2 pi was typically the period for a regular sine wave to complete itself. Was 2 pi. So we're asking what is that distance. But now that the axis is going to be representing time, we're saying exactly how long in time does it take for the wave to complete itself. So the period, if you remember, that was 2 pi over w. And we have something new that we're going to go over called the frequency. Right. And this is just the reciprocal of the period, w over 2 pi. Basically, what the frequency was going to tell us is how many times per second does this wave complete itself, right? How many times per second does this wave complete itself? All right, that's what the frequency is giving us. They'll say like the number of oscillations per second, or really doesn't, not necessarily per second, per unit of time. It'll most likely be a second, but so these are the equations we're dealing with. And let's go ahead and look at an example. I'll take a picture of it and the directions. So our first one. Okay. So here's the description, and let me take a picture of the spring. All right. So here's what we're working with. A lot of information here. It says, build a model for an object in harmonic motion. Suppose that an object attached to a coiled spring is pulled down a distance of 5 inches from its rest position and then released. If the time for one oscillation is 3 seconds, develop a model that relates the displacement d of the object from its rest position after time t in seconds. Assume no friction. Assuming no friction meaning like it's not going to slow down. Obviously, if you pull back a normal spring and let go, it's not going to continue to go at the same rate, same distance forever. It's going to eventually slow down and rest. We're assuming that's not happening here. So the motion of the object is simple harmonic. when the object is released at t0, the displacement of the object from rest position is -5 units. Since the object was pulled down, because d is -5 when t is 0, it's easy to use the cosine function. So really deciding whether we're using sine or cosine is all in the description of the problem. This says it's pulled down and then released. So if you remember our graphs, remember sine starts at 0 and looks like this, okay? And cosine will start at the top and look like this. That's one period. Now, if it starts at the bottom, that's just negative cosine. It's been flipped. So that's basically what we're using here as a negative cosine function. So we should have d equals, now it says this displacement, the maximum displacement from the rest position is 5. So that's going to be my amplitude, right? So we should have -5, again, because it starts at the bottom, cosine. Now we need to figure out what is w. Back at the top, what did it say about time? I froze here. Okay, we're good. It said the time for one oscillation is 3 seconds. So the time for it to complete itself, the wave one time, is 3 seconds. So the period then is 3. So what does that make w when we plug that into the equation? 2 pi over w. Okay, we're solving that equation. So multiply both sides by w, you should have 3w equals 2 pi, divide by 3, w equals 2 pi over 3. Okay, and that's going to go into our equation. And really that was it. This is the model for that description. This is 2 pi over 3 times t, right? That describes the motion of that spring, okay, pulled down from rest position and let go. Okay, that's this guy. So basically, we could enter a certain amount of time, say like 2 seconds, 3 seconds, and this d would tell us how far away from rest position is the spring at that moment. Okay, so that's what we're doing here. We are going to do another one, but hope this is making sense. Let's do one more example. It'll be a shorter lesson. This is going to be for both days. We're not really doing a double lesson this week. So you're welcome. You're welcome. Say it again. Let's go over this next one. All right. Analyze simple harmonic motion. Suppose that the displacement d in meters of an object at time t in seconds satisfies the equation d equals 10 sine 5t. Right? Let's answer these 4 parts. So describe the motion of the object. This is pretty much going to be the same answer for all the examples we're doing. It's simple harmonic. Okay. That is simple harmonic motion. All right. Part B. What is the maximum displacement from its resting position? Maximum displacement is just the amplitude. We can see here that A is going to be 10, so this is 10. C. What is the time required for one oscillation? Remember, that is the frequency, or sorry, not the frequency, the period, and the period is 2 pi over w. So if w is 5, 2 pi over 5, that's going to be my answer there. So that is p equals 2 pi over 5. That's no reducing to be done there. And then d, what is the frequency? That's just the reciprocal of the period. So how many times will this complete itself in 1 second? That is going to be 5 over 2 pi. All right, that's it. What's that? Not that bad, right? Let me know if you guys have questions. Yeah, that's all I want to do. Let me know if you guys have questions. Hope that makes sense. Just those two quick examples should be a pretty quick lesson for you guys. Don't forget, this will we'll have a progress check on Friday for the 2 lessons this week. And this is all we're going to do in Chapter 8, so we will be starting a new lesson next week. So yeah, let me know how it goes. Miss you guys. Hope you're doing well. And take it easy. Peace.